Morning students, welcome back to the physics department. We all know that we were seeing the 14th chapter, that is Semiconductor Electronics, and in that we have already seen the diode part. We were studying about that. We read about its biasing, forward biasing, reverse biasing, then certain applications. The diode used as a rectifier, that was the main application what we saw. Okay. As a rectifier, in that also half wave rectifier and full wave rectifier, both we have seen. Okay, now having studied the diode as a rectifier, there are many other applications of diode. Okay, it is used in nowadays, it is used in many devices. In that, certain devices we will study in this class. Okay, now those devices are known as optoelectronic devices. Optoelectronic devices. Some special functions of the diodes we are studying here. Okay, keep this in mind. Optoelectronic devices means what? You have read the definition here. What do you mean by optoelectronic devices? See, electrons are there. Opto means light energy, isn't it? Opto means, literally it means light energy. So what are optoelectronic devices? The devices that generate the charge carriers. Charge carriers in sense electrons, isn't it? Please take this definition. The devices that generate the charge carriers on incidence of a photon or light energy. Light energy is nothing but photon, isn't it? Photon, h nu. You have studied this in Einstein's theory. You know the photoelectric effect. Okay, so h nu energy falls on the surface from the light, isn't it? So the light energy is in the form of packets called as photons, having the energy h into nu. H is the Planck's constant, nu is the frequency of that. So these photons, when they are incident on a diode, okay, when they are incident on a diode, there is the generation of many charge carriers, or in sense you can say electrons. So due to light, the electrons are being generated. Those devices are known as optoelectronic devices. Understanding? May I repeat the definition? Please take it down. The devices that generate the charge carriers due to the incidence of light energy are known as optoelectronic devices. Okay. In that, actually, three devices we have to study. Three devices are there for your syllabus. One is photodiode, okay, then LEDs, you all know, light emitting diodes, and the solar cells. So these three we need to study today. Okay, fine. So let us take these two later. First, let us come to photodiode. What is photodiode? Okay. So as the name itself indicates, there is the photon being incident and the diode is present. That is photodiode. Okay. Please understand. See the setup. There is a diode, PN junction, correct? And photons of energy h nu are being incident on it. Okay. So this is the setup. Now can you please identify which biasing we have used here? Can you please identify that? See the diagram and guess. P is connected to the negative terminal of the battery. N is connected to the positive terminal of the battery. In sense, this is under reverse bias. Am I right? This diode is working under reverse bias conditions. Right? So, what is photodiode? What is photodiode? It is a device. It is a reverse bias PN junction, you can say. It is a reverse bias PN junction, okay, which will generate the current on incidence of photon. Okay, means when the photon of energy h nu is being incident on the PN junction diode under reverse bias condition, okay, it will generate the current, or it will generate the flow of charge carriers. Flow of charge carriers is nothing but current, isn't it? So when you are illuminating the PN junction diode, this is called as illumination. That means you are sending the light energy on that. Okay. So when you are illuminating the PN junction which is under reverse bias, okay, if it creates the flow of charge carriers or the flow of current, such a device is known as photodiode. Okay, that is the thing. You have to form the definition. I have explained it. You have to form a correct definition out of it. Okay, try this. If you don't get, please message me. I will tell the definition later. Okay. Now you know that it is working in reverse bias. Can we see the working of this? Try to concentrate how this works. Okay. Now the setup, as you know, is under reverse bias condition. Fine. In reverse bias, which current flows? You all know. Reverse saturation current flows in the reverse bias condition. Am I right? Reverse saturation current. Now this reverse saturation current will be due to what? Due to which type of carriers? Due to minority charge carriers. Am I right? Due to minority charge carriers, there will be a small amount of reverse saturation current in reverse bias. You all know this, isn't it? You have learned the reverse biasing. When you bias it reversely, when you bias the diode reversely, there will be a small amount of current flowing, that too because of the minority charge carriers. What do you mean by minority charge carriers? In P side, electrons are the minority charge carriers because holes will be in majority here. First thing. In N side, holes are the majority charge carriers because electrons will be more here. Okay. So here minority charge carriers are electrons. Here the minority charge carriers are holes. Am I right? Now due to the minority charge carriers, there will be a small flow of current called as reverse saturation current in reverse biasing. We know this. Okay. Now consider this H nu is not there. Okay. You have not incident any photon of any energy to the diode. Okay. Now can it pass through the junction in reverse bias? Can it pass through this potential barrier? This is potential barrier, isn't it? This is potential barrier. In reverse bias, the width of the potential barrier will be quite large. Okay. Your charge carrier cannot cross the potential barrier, isn't it? Cannot cross the potential barrier. Okay. Now, what happens when you incident a photon? When you incident a packet of light energy, H nu, when it is incident, what happens is there will be the electron. Okay, so there is an electron somewhere. There is an electron. This will get enough energy to jump from the valence band to the conduction band. Am I right? Whenever you are giving energy to an electron, it will jump from valence band to the conduction band, isn't it? This is natural. So when it jumps to the conduction band, okay, it is somewhere jumping. What happens is an electron hole pair is generated. Please remember this. This is the working I am explaining. Okay, when a photon of energy H nu is incident on a PN junction diode, one electron will get enough energy to jump from valence band to the conduction band. Okay, so it crosses the junction now. It has got energy. It will cross the junction. When it crosses, there will be a hole. Okay, somewhere there will be a hole. Or electron from this also can cross. Any electron. When it crosses, since it will be negative, a hole on the other side will attract it. A hole on the other side will attract the electron. So electron hole pair is generated. Okay, electron hole pair is generated. Fine. This is the example of one electron. But when you are continuously supplying the light energy, many electrons will be having the energy to jump to the conduction band. Okay, they all will cross the junction and many electron hole pairs will be generated. Am I right? Many electron hole pairs will be generated. Okay, now this is stopped. Many electron hole pairs are there. Okay, but here the potential difference is there, no? The junction potential. It will be having a negative energy, isn't it? Means it will be having its own electric field or potential it will be having. This diagram you already know. Okay. So now this will try to separate the electron hole pairs. This will try to separate the electron hole pairs because it is the negative energy. Okay, it is the negative energy. They will be drifted or they will be trying to separate. Okay, now when they are getting separated, they will be moving away from each other. The electrons and holes will be moving away from each other due to the negative potential, that potential barrier, that junction potential difference. Okay, when they are moving, they constitute what? They constitute the current, isn't it? Which type of current it is? Reverse saturation current, because the charge carriers will be moved in such a way that they are minority in that region. Means minority charge carriers will be moving. Just understand that minority charge carriers will be moving. So when minority charge carriers are moving, the reverse saturation current has to what? Has to increase. Correct? Has to increase. So in this way, whenever the light is incident on a diode, the reverse saturation current increases. This is the current meter. Ammeter you call it as. Okay, it is reading the current. What happens in this? Whenever you are incidenting the photon, the current is being increased. The reverse saturation current is being increased. This is the concept. This is the working. Are you understanding? Just I will summarize it once. When you are incidenting a light of energy h nu, the electron will get enough energy to jump from valence band to the conduction band. Okay. When it jumps, it crosses the junction potential. When it crosses the junction potential, it forms an electron hole pair. Electron hole pair is generated. Okay. When the electron hole pair is generated, there will be a negative potential. There will be an electric field set up in the negative direction, which will try to separate the electron hole pairs. And when they are getting separated, they constitute a current. Because there is a flow of charge carrier. And which charge carrier? Minority charge carrier. So there is more minority charge carrier flow is being constituted in the PN junction. That means there is more reverse saturation current flowing in the PN junction. So whenever the light is incident, the reverse saturation current increases. This is photodiode. You give it light, the current flows, but in reverse biased mode. Okay, that is photodiode. Now what are the applications of the photodiode? Where do you use this? You use this in receivers for the remote. Okay, I am sending a signal from the remote. The receiver will be in TV or something. Okay, the receiver will be having the photodiode. Why? I am sending the signal, that is a photon of energy. It captures and reverse flow is happening. So the current, whatever that the work has to be done there in TV, that should be done due to a current. How does that current flow? From remote, I am sending the signal and the reverse saturation current flows and the work is being done. The channel is being changed or the volume is being increased. Whatever is being done, that is done. Now, receivers for remote have this photodiode and photodetector. Okay, means to detect the optical signals, to detect from where the light signal is coming. That is called as photodetector. Okay, that uses the photodiode. And lastly, camera light meters and clock radios. You have to remember the applications of the photodiodes. Normally, 1 mark or 2 marks, these are asked. Okay, the principle also can be asked for 2 marks. Fine. So please take it down, take the diagram and also the applications. Pause the video here, take the applications and then we will go to the next type of optoelectronic device. So students, let us now see the second type of electronic device, optoelectronic device, that is LED. What is the full form of LED? You all know, so I have not written it. Light emitting diode. Okay, light emitting diode. Now where do you use it? You use it on all the screens, almost all the screens what you see right now on the in the laptop, in the TV, everywhere you use this LEDs. Even in the bulbs you use LEDs, correct? Light emitting diodes. Means there are diodes Okay, they are emitting light, isn't it? How is this possible now? That is the thing. Okay, what do you do now? See, light emitting diode is a forward biased diode. First, you have to remember this. It is a forward biased diode. Okay, it is working in forward biased. What happens is, when you give energy, okay, electrical energy are supplying, isn't it, to any electronic device, be it TV or something, you are giving the electrical energy. When you are providing the energy, okay, again the electron will move to the conduction band from the valence band. This is natural process. You please remember this. Whenever you are supplying energy, your electron will be moving from the valence band to conduction band. Now, the special case here is LEDs are heavily doped. Heavily doped. Doped means what? Doping, you all know, adding the impurities, isn't it? So trivalent and pentavalent impurities are added. Now, the trivalent and pentavalent impurities are added in high quantity. Heavily doping is done. Okay, means there are many charge carriers. Okay, so when you provide some energy to the electrons, okay, the electron hole pair will be generated. Correct? The electron hole pair will be generated. But since it is heavily doped, many electron hole pairs are generated, isn't it? Many electron hole pairs are generated. So an electron is there, a hole is there, okay, it is getting the energy, so they are getting paired up. Okay, now when they get paired up, okay, they have to release the photon of energy. Okay, electron is unstable, correct? Electron is unstable. You are supplying the energy, it becomes unstable. It goes and pairs up with the hole. Okay, now when it is getting paired up, it should release the energy, and that energy is released in the form of a photon, nothing but light. Correct? So when the electron hole is being paired, one light photon or one packet of energy is coming out, and that is in the form of light. So light is being emitted by the diode in a forward biased condition. This is the thing. So it is called as light emitting diode. When the intensity of the energy you provide is small, LED, the light emitted is also small. When you are giving high energy, more light is coming out. This is the thing. And the color of the light can also be considered. The color of the light depends on the material you are using, which semiconductor material you are using. Based on that, the color also can be changed. Okay, so please remember, when you are giving the energy, the electron hole pairs are generated. When the electron gets paired up with a hole, it should release some energy, and that energy is released in the form of a photon. That is nothing but the light energy. So the light is being emitted. Okay, so on the screen of TV or of your mobile, everywhere, or computer, the LEDs are used. Okay, that will do what? When they receive some energy, they emit the light and they illuminate the object. Okay, the uses of LED, many are there. A bunch of LEDs can be seen in traffic signals, right? Red light, blue, yellow, okay, green. All those colored LEDs can be used. Okay, then in calculators, in measurement displays means there is like 10, 9, 8, 7 that will be being displayed, isn't it? On the screen, it will be being displayed using the LEDs. Okay, then burglar alarm systems and optical communication, and also message displays. You display the message. Where do you display? In airports or in railway stations, okay, in bus stands, everywhere the messages of this particular plane is coming at this time, departure, arrival, everything is being displayed, and that message is being displayed using LEDs. This is the second type of optoelectronic device. Please take the uses. These are mainly asked here. Uses are asked for 2 marks. Please take this. Okay students, now the last part is the third optoelectronic device, that is solar cells. Okay, solar cells are also known as photovoltaic cells. Please remember this name also. They are known as photovoltaic cells. Okay, that means here also an incident of photon, the voltage is being generated. Okay, on incident of photon, the voltage is being generated. So it is called as photovoltaic cell. Means it is giving the power. It is not taking the power. Okay, please remember, it is not taking the power. When the photon is incident on the PN junction, that is diode, it is giving the voltage, it is giving the power to the other materials so that they get the energy. That is photovoltaic cell. I think many of the houses on the top, solar cells are situated. Those tap the solar energy to provide electricity to the bulb and fan and everything that is there in homes, isn't it? That is solar cell. Okay. Now, we need to understand how does this work first. Okay. The solar cell, please remember, also is working in reverse bias condition. Okay. First, this is the setup. The PN junction is there. Okay. On the top, the electrodes, metallic electrodes are placed. Okay. On the top of that solar cell, that is trapping the energy, the solar energy. It is trapping. Okay. So that is given the front contact. Okay, front contact. It will be having two contacts, right? So front contact. And the PN junction is having the back contact. Okay. Now what happens? Say the process happens in these three steps. The first step is generation. The first step is generation. What is being generated? You all know. When the photon, okay. Now remember everywhere, please remember this, your h nu should always be greater than the energy gap. Only then it will be generated. This you already understood, so I didn't explain. See, energy gap, the silicon will be having the energy gap of 0.7 volt, correct? Germanium of 0.3 volt. You all know this. Okay, the energy, the band gap between the conduction band and the valence band. Okay, your h nu should be having more energy than the band gap. Then what happens? The PN junction, okay, when it receives such a high energy photon, the electrons will be getting the energy to jump from valence band to the conduction band, correct? And the generation of what? The generation of electron hole pairs takes place, correct? Electron holes are being paired up again. This is depletion region. So electron holes are being paired up. Okay. When the electron hole pair is generated, okay, due to the voltage of the depletion layer, they have to be separated. Okay. The second step that is happening is separation. Separation of what? Separation of electrons and holes. Okay. Electrons and holes are separated due to this potential junction. Okay. Due to this potential, they are being separated. When they are separated, electrons move to n side and the holes move to p side. Correct? Holes move to p side, electrons move to n side. But the last thing is collection. The collection. You have got two electrodes here. Okay, two electrodes. Front contact is there, back contact is there. Okay, means the holes which are coming out are collected by the back contact. The electrons which are coming out are collected by the front contact. Means the holes and electrons are moving. Okay, the holes and electrons are moving. Your P is becoming more and more positive. Your N is becoming more and more negative. That will give rise to photo voltage. Okay, that will give rise to photovoltage. P, here holes are being collected, correct, at the back contact. At the front contact, the electrons are being collected. Okay, when you are collecting the two separate polarities charge carriers, the voltage is being generated, and that voltage you call it as photovoltage. Why? Because due to the photons, this voltage is being developed. Okay, and that voltage you can supply to any other device, and it will supply the power to that device. So using the solar energy, you are generating the photovoltage. In sense, you are generating the power to be supplied to the other devices. Okay, now the uses you can see to power the electronic devices in satellites. In satellites, you do not have a battery to connect. You have to tap the solar energy and give the power to the electronic devices situated in the satellite, isn't it? For that, these solar cells have to be used in the satellite. Okay, then to supply power to the calculators, some of our devices, solar energy is tapped, and to supply power to our houses, many devices in our houses also can use this solar cell. Okay, now these are the three optoelectronic devices which are there for your syllabus. You have to mention the uses. Uses are mainly asked. Okay, concentrate on them, and you have to know the principle and the setup diagram of all these things. I hope all the three optoelectronic devices are clear to you. Now we come to the last part of this chapter, that is digital electronics and logic gates. Okay, now you have heard this word digital everywhere. You see everything is being digitalized. What do you mean by digital? What is that meaning? Okay, it should be something related to the signal, isn't it? Digital signals we say. What do you mean by digital signals? See, when you were drawing the waveform for the rectifier and all, it was how it was? It was a sine wave like this, correct? It was a sine wave. Okay, means you do not have a fixed value. Here is 0, 0.1, 0.2, 0.3, it will move up to 1, again it will reduce, again it can go from minus 0.1, minus 0.2 like this. Okay, again it can increase. Now this is called as analog signal. Okay, means continuous signal is there. That is analog signal. Continuously there is some value. Okay, that is analog signal. But digital signal is not like that. Digital signal will have the discrete values. Discrete values. Okay, only two values are possible in the digital signals, either 0 or 1. Means off or on. 1 means on, 0 means off. Only two values possible. Okay, the waveform will be something like, see, 0, 1. Okay, how much time you want to remain it as 1? It will remain. Again it will directly be 0. Nothing like 0.5, 0.6, no values like this. Discrete values. 0, 1. See, until this time it is 0. For this time it is 1. Again 0. Again 1. For this time. Again 0. Like this, analog signal is having many continuous values. Here it is not continuous. It is in the discrete form. But it will be either 0 or 1 or 0 or 1 like this. Okay. This is digital device. These are called as digital devices, which will be having the discrete values, not the continuous values. Continuous waveforms are not there. Okay, the waveforms are in discrete manner. Okay, so that is digital electronics. Now the branch which deals with the digital devices is digital electronics. Okay, based on that we study some digital circuits which are known as logic gates. Okay, which are known as logic gates. Now what are these logic gates? Logic gates are the digital devices, correct? Logic gates are the digital devices or digital circuits, okay, which have got a logical relationship between the input and output. Please take down this definition. Logic gates are the digital devices or digital circuits which have got a logical relationship between input and output. This is input and this is output. Okay. Means, see, the relationship will be like if input is 0. Okay. If input is 0, output is 1. I prepare such a device where if I give 0 as the input, it should show 1 as the output. If I give 1 as the input, it should show 0 as the output. Okay, such a device I can form. Okay, and something like if there are two inputs. Okay, if there are two inputs, if I give both the inputs as 1, the output should be 1. I can have some logical relationships like this, isn't it? If both the inputs are 0, then the output will be 0. Like this I can have. Many relationships I can have. Okay. Now based on these combinations of relationships, there are certain logic gates being formed. Okay. Many logic gates are there. Out of them, 5 logic gates we are trying to learn in this syllabus. Okay. Only 5 logic gates. Let us take one by one. See, every logic gate will have a symbol, okay, and the truth table. Truth table means what? Truth table is the combination of input and output. Okay, for what input, what output you get. If you write that, that is called as truth table. Okay, so first gate that we study is NOT gate. Okay, NOT gate. NOT gate means what? It is also called as inverter. Okay. Inversion. What do you mean by inversion? Reverse process. Isn't it? Means, see, the input, okay, and the output. Fine. Truth table I am drawing. Okay, this is the truth table. If 0 is the input, 1 is my output. Okay. If 1 is the input, 0 is my output. If a gate behaves like this, okay, I have a digital circuit. If I give 1 to it, it gives me 0. If I give 0 to it, it gives the output as 1. That circuit is known as NOT gate. Okay. And please remember the symbol. This is NOT gate. Okay. If X is the input, say, this is the input part. Okay. If X is coming as the input, what will be the output? Reverse of this. Reverse of this is denoted as X bar. X bar. Okay. I think you have studied it in maths. Fine. X bar will be 1. If your X is 1, your X bar will be 0. Sum means whatever input you give, the output you get reversed of it. This logic gate you call it as NOT gate. Okay. NOT gate. Fine. Please pause the video here and take this. Fine. Now, let us go to the next gate. And that is AND gate. Okay, second one, AND gate. Fine, AND gate. So how this AND gate works? AND gate is a 2 input gate. Minimum 2 inputs are required. Okay, 3, 4 can also be there. Minimum 2 inputs are required. Say A and B. 2 inputs are there. Okay, and you get an output. Output you say as Y. Let us consider as Y. Okay. Now, what is the relation of AND gate is, I'll just write the truth table. You try to find the relationship. Okay. So, these are the possibilities. Okay. Only zeros and ones are there. Out of that, how many combinations you can form? 2 entities you will have. How many combinations are possible? 4 combinations are possible. Either both can be 0 or 0, 1 or this one 0 or both 1. Okay. Now your output is in such a way that, see, this is the output. Can you now form the logical relationship of AND gate? When can you say that it is AND gate? You can say it as AND gate when only if both the inputs are on means 1, only if both the inputs are 1, the output is 1. Only if both the inputs are high, the output is high. Otherwise, it is low. Okay. If either only one input is high, it will not be high. Okay. Only if both the inputs are high, it will be high. That is AND gate. Okay. Now the symbol of this you need to remember. This is A, this is B. AND gate symbol is like this. AND gate symbol is like this. Okay. Can you compare this with your normal multiplication? 0 into 0 is 0. 0 into 1 is 0 itself, isn't it? 1 into 0 is 0. Only 1 into 1 is 1. Correct? So, your AND gate follows the multiplication. Dot means multiplication. A dot B. Correct? A dot B means multiplication. Your AND gate always follow the logical multiplication. Okay. So, it will be high. The output will be 1 only if both the inputs are 1. Otherwise, it will be 0. So, normally the question will be like, draw the symbol of AND gate or draw the truth table of AND gate. 1 mark, 2 mark, these can be asked. Okay. And the third gate is reverse of this. Reverse of this. You call it as NAND gate. Okay. You call it as NAND gate. NAND gate will be like completely reverse of AND. Okay. See, symbol will be something like this. And a bubble. This bubble will represent that it is being inverted. Okay. Whatever output is there for AND, it is being inverted. That is NAND. Okay. So, if it is A, B, okay, Y, fine. How it will be the truth table? So, input A, B and output. Correct? So, see the combinations 0, 0, 0, 1, 1, 0, 1, 1. Okay. Now, how the output will be? Your output is Y. How it will be? See, reverse of this I have said. Reverse of this means 1, 1, 1, 0. Because here 0, 0, 0, 1 is there, no? So 1, 1, 1, 0. Can you state the relationship? You can state it as the logic gate can be called as NAND gate if both the inputs are high and you are getting the output as low. Okay, when do you get the output as low? Only when the inputs are high. At that time you get the output as low. Otherwise it is always high. See, high means 1, low means 0. Please remember. Okay, you have to just remember this truth table. Nothing else. It is just reverse of this AND gate. Okay, means if both the inputs are high, the output is low. Otherwise it is high. That is NAND gate. How it is? It is like A into B bar. Correct? A into B is your AND gate. What is NAND gate? A into B bar. Bar means reverse of that. Whatever A into B is possible. See, 0 into 0 is what? 0. A into B. Bar of that is, complement of that is 1. So, A into B bar. It is required. That is NAND gate. Okay. So, please take down AND gate and NAND gate. Pause this video and take down. Now, let us go to the next. So, last two gates are remaining. One is OR gate and another is NOR gate. The reverse of that. Okay. So, the fourth one is OR gate. OR gate. I'll just write the relationship. Okay. You try to make out how to state it. Which are the combinations possible? 0, 0, 0, 1, 1, 0, 1, 1. Okay. The output will be 0, 1, 1, 1. This will be the output. When can you say that such a situation can exist? You can say if either of the input is high, then the output is high. If either of the input or both the input, if they are high, the output is always high. It will be low only if both the inputs are low. This is OR gate. Means in A or B, if A is high, then also your output is high. If B is high, then also your output is high. If both are high, then also it is high. It is low only if both A and B are low. Will it follow your addition? 0 plus 0, 0. 0 plus 1 also 1. 1 plus 0 also 1. 1 plus 1 cannot be 2 here logically because it is binary number. You can have only two things, 0 or 1, isn't it? So, it follows logical addition. You call it as logical addition. Okay. What is the symbol of this? Say A, B. Okay. This is the symbol of OR gate. Okay. A, B. A leaf-like symbol has to be drawn for the output. This is the symbol of OR gate. You have to understand that. Okay. And the last one is NOR gate. Now you can easily know what is NOR. Exactly the complement of OR gate. The reverse of OR gate. How can we draw this? Symbol of NOR gate. OR is there and a bubble over. Okay. A, B and Y. What will be your Y? Say, let us understand here in the truth table. 0, 0, okay, 0, 1, 1, 0, 1, 1. It is reverse of OR gate I am saying. So the output will be 1, 0, 0, 0. Means what? Only if both the inputs, only if both the inputs are low, you are getting the output high. For all the others, your output is low. Means in A or B, if either of this is 1, then also it will be low only. The reverse of this OR gate, isn't it? So you can say that your Y is equal to A plus B whole bar. A plus B is your OR gate, normal logical addition. It is the complement of that normal logical addition. A plus B whole bar. Okay. So this is about OR gate and NOR gate. Now these are the basic concepts that you are studying in digital electronics and logic gates. Okay. So this is about the 14th chapter, that is semiconductor electronics. You can please go on revising the things. Please let me know if any doubts are there. You have my number. Just message or call and ask and clarify your doubts. Whatever the syllabus is prescribed for this academic year 2020, those concepts we have studied in this session. Okay. Thanks for your cooperation.